Have you ever stopped to think about how scientists can know exactly what's in a substance and how much of it just by shining a light through it? I mean, it sounds a little like magic, right? But it's actually pure science, and it's all governed by a really beautiful and simple principle, the Beer-Lambert Law.
So here's what we're going to get into. We'll start by, shining a light on the core concept itself. Then we'll dig into the story behind it. It's actually a tale of two different laws. After that, we'll put it all together in the unified equation, and then comes the really cool part. We'll see how it's used in everything from analyzing your blood to understanding our atmosphere. And finally, we'll look at where the law has its limits, where it starts to bend a little.
Okay, so let's jump right in. At its heart, the Beer-Lambert law is all about one simple thing: light getting dimmer when it passes through something. But here's the kicker. It's not just about things getting darker. It's about using that change in brightness as an incredibly precise tool for measurement.
And here's the more official take on it. The law relates the attenuation of light, which is really just a fancy word for light getting weaker, to the properties of whatever material it's traveling through. Or to put it simply, the more stuff you have in the light's path, the more that light gets absorbed. It's an idea that just makes sense, but it's also incredibly powerful. Now, a law of this important doesn't just pop into existence. Nope. This one was built piece by piece over more than 100 years by three key scientists. It's a classic story of standing on the shoulders of giants.
Our journey starts way back in 1729 with a guy named Pierre Bouguer. He was the first to notice that the thickness of a substance was directly tied to how much light it soaked up. Then, about 30 years later, Johann Heinrich Lambert took that idea and ran with it, formalizing the link between how much light is absorbed and the path it has to travel. And then, get this, almost a century later, in 1852, August Beer comes along and adds the final, crucial piece of the puzzle. He's the one who connected absorbance to the concentration of the sample.
So you can see how these two core ideas eventually came together. On one hand, you have Lambert's law, which says the longer the journey for the light, the more of it gets absorbed. Think about walking through a forest, right? The deeper you go, the darker it gets. Then you've got Beer's law, which says the more concentrated the substance is, the more light gets absorbed. That's kind of like how dense the forest is. If the trees are packed tightly together, they'll block more light, even if you don't walk very far. All right, so we've got these two separate but obviously related ideas. The next logical step, and what was truly brilliant, was mashing them together into one of the most useful equations in all of analytical chemistry.
And here's the unified idea, just in plain English. It's so elegant. It basically says that both the distance the light travels and how much stuff is dissolved in the substance are directly proportional to how much light gets absorbed. It's the grand unification of Lambert's and Beer's work.
And boom, here it is in all its mathematical glory, the Beer-Lambert law equation. Now, I know it might look a little intimidating with the E and the exponent, but trust me, the idea behind it is exactly what we've been talking about. Let's just quickly break down what each part means.
It's actually really straightforward. I is just the intensity of the light that actually makes it through to the other side. I naught is the initial intensity, what you started with. X is that path length we talked about, how thick the sample is. And mu, that Greek letter, is the absorption coefficient. That's just a number that tells you how good a specific substance is at absorbing light. And that's it. The equation just calculates how much the intensity drops off.
Okay, so we've got this elegant law that took centuries to build, and we've got this neat little equation, but why does it matter? I mean, who cares? Well, it turns out this law is used absolutely everywhere, from a microscopic level all the way up to a planetary scale.
The two biggest arenas for the Beer-Lambert law are analytical chemistry, where it's just fundamental for measuring what's in a sample, and atmospheric science, where it helps us understand the very air we breathe and the sunlight that keeps our planet warm.
Let's make this super concrete. Say you're in a hospital, and they need to measure something like bilirubin levels in a blood sample. They use a machine called a spectrophotometer. This machine shines a specific wavelength of light through the blood sample and measures how much comes out the other side. And it's the perfect tool because it's fast, it doesn't harm the sample, and by plugging that light measurement into the Beer-Lambert equation, it can instantly tell doctors the exact concentration they need to know. It's used for critical diagnoses every single day. And what's amazing is that this law scales up beautifully. To figure out how much of the sun's radiation actually reaches the Earth's surface, scientists use a souped-up version of the Beer-Lambert law. It's the same core principle, but it has to account for all the different things in our atmosphere that absorb light. You've got ozone, water vapor, nitrogen dioxide, dust, you name it. But the fundamental idea is exactly the same. Light comes in, stuff gets in the way, and less light comes out. Now, no law in science is a magic wand, right? They're all models of reality. And every model has its limits. The Beer-Lambert law is incredibly accurate and super reliable, but only under the right conditions. So what's the biggest limitation? It really comes down to concentration. The law works best and is most accurate for solutions that are pretty dilute. Specifically, we're talking about concentrations below 10 millimolar. That's just a standard chemistry unit for how much stuff is dissolved. That's the sweet spot where everything lines up perfectly.
So what happens if you go above that concentration? Well, when things get more crowded, the individual particles in the solution start getting so close that they actually interact with each other. You get these electrostatic forces that change how they absorb light, and that causes the results to stray from what the simple law predicts. Basically, the model starts to break down because reality just got a little more complicated.
So, after digging into its history, its math, its amazing applications, and even its limits, what's the one big thing you should really take away from all this?
Well, here are the key takeaways. First off, the Beer-Lambert law is a simple but powerful rule that connects how much light is absorbed to both how far that light travels and how concentrated the substance is. Next, remember it's a great example of scientific progress, built over 120 years by Bouguer, Lambert, and Beer. Also, it has incredibly important real-world uses, from analyzing your blood to modeling our entire atmosphere. And finally, always keep in mind that it's a tool that works best under specific conditions, mainly at low concentrations.
You know, the story of the Beer-Lambert law is pretty amazing. It shows how a simple observation that things cast shadows can be transformed into a precise scientific instrument that lets us see the invisible. It really makes you wonder, what other secrets are hiding all around us, in plain sight, just waiting for someone to shine the right light on them?